Good morning, everyone. I'm Wang, come from Chinese University of Hong Kong. The title of my talk is Theoretical Quantum Control for Interaction of Particles. This work initially presents theoretical quantum control for polyparticle in a nuclear interaction in the framework of a variation method. Optimal control theory for interactive particles is considered in Hilbert space. Full proof of the existence of quantum optical control is supplied in general manner. At last, a quantum optical control system is deduced. We can cite this work at the GSIM Annual Conference of Osaka University, 2009. The background of this work is we can find it is incredible if lacking consideration for particle interacting about study of control quantum system. Even just the preparation of quantum state of particle, atoms, molecules, nanoparticles in the evaluation of interaction is nonsense in most of the cases. What is natural watch in treating problems is to trace the control of particles they are interacting each other. The goal of this paper is to do theoretical issue for quantum control of interactive particles at the Yugawa copy. Where the control of the interacted situation is much more difficult than a free particle, a great deal question would be occurred in this way. Lastly, the rising problem of control force and interactive force are in here. Control force laser parcel internal force are greater than interaction of particle. This makes a total break, destroying the neutral particle structure, just like break interactive bonds in chemical reaction of molecules. Second is control force are two equal force, carry low energy to change the interstructure. It can make an unlikely type variation. This does not mean control what we meant. Third is control force is still very considerable than inner interaction force. It can make the interaction change in a sufficient and free way. This meets satisfaction for needs what we consider as control system control. In fact, above issue are crucial if we separate from real experimental advantages. In practice, the force of two objects is regarded as a exchange one or more particles, meson, neutrino, electron, one injection to others, particle transfer momentum and energy return to objects. Although we know the fundamental interaction is divided into four forces. Force is the force is the strong force, the second is weak force, and the third is electromagnetic force. The force is the gravity force. We repeated it detailing here. The strong nuclear force is a force between two quarks hold nucleon and protons together in nucleus, such as gluons, colors, and weights. Quarks are strong force person. Neutrino consists of a quark combined UUDT, proton UUD, and meson UU by D divided. This strong force can be regarded as a quark injected inside the nucleus. The theory of a strong interaction among quarks and gluons is called quantum thermodynamics. This most important contributions are in these four papers. Second, weak nuclear force, it means the electron and the neutrinos, such as force between W and Z boson. The third is electromagnetic force, two electrons, such as the proton interactions. Last one is gravity force, actual force between two objects. What we interested can see that the control particles they are interaction in Euclid couples, whether we can construct appropriate physics control models. What are the theoretical analysis and the numerical result of these questions just to solve in this work? First, we introduce the Klein-Gordon-Schrödinger equation. Quantum system control of Euclid interaction is our target. It is well known that the exchange particles among the neutrons and protons. This thanks to the Euclid interaction, which is successfully predicted in 1930s and soon after verified by physics experiment at the discovery of the meson pi. Our work is interested in the quantum system consists of polyneutrons, polyprotons, and polymesons, and different external control forces. We suppose MPN be the number of the involved protons, neutrinos, and meson, neutrons, and mesons. IGL are positive integer, and the side the I is between the 1 and MP, J between 1 and NN, L between 1 and NM. Quantum system MP's proton consists of MP proton, NN neutron, and NM mesons. MP control acted at the proton, and NM control acted at the meson is our control objective. As usual, denote MP, NM as the mass of proton, neutrons, and meson. We denote C as the speed of light, and H is reduced Planck's constant. E is the charge of a proton, and E permeate is the charge of meson. Let capture omega be the open bounded side in the R's space, and Q equal 0T times K omega for T positive. The I is the unsigned part of a complex function. In this way, we can describe the Euclid interaction in the form of a multi-Klein-Gordon-Schrödinger equation in the equation 1. The first one equation is the proton equation, and the second one is the neutron equation. The last one is the meson equation. The initial function is given in this form, where psi pi and psi ny complex Wallace functions represent the probability amplitude of proton and neutrons field. Phi I is a real Wallace function representing the probability amplitude of meson field. System 1 represents the interactions through Euclid couplings. Here U and V is the control input of a proton and meson, which is external neutral short like the path in real laboratory experiment. We need to remark one for the first two equations is separating our equation because of the neutron is natural, so the control is not involved in the equation, and the last the result is the first and the third equation involve control. For the interpretation using Feynman formulation, and like this in figure 1 and figure 2. This is the interaction from N to P plus missing pattern, and this one is p to n plus 1 in the form. In our study, is considered the first one, case 1. Our future work 17 is for the case of a missing exchange export. Let's do mathematical sightings. To do theoretical analysis, use the variation method under the frameworks in Hilbert space. We have some work published on the quantum control. Let's review some of them. First of all, our paper 1.8 is for, we consider the single particle case. And also we consider a perturbation control case. The third is two people for single particle, and the last one is a mixed exchange export. We are recent work for nuclear reactions. The aim of this work is to do full proof of optimal control theory for quantum system described by Klein-Gordon-Schrödinger equation. First, we give mathematical sightings, introduce two Hilbert space H equal 2 omega and V equal H 01 omega, and usual and inner product. Therefore, the embedding of Klein-Gordon trip space. Klein-Gordon trips are continuous, dense, and compact. Above citing make us to analyze the variational method as H. First of all, we define the weak solution form and the solution space as usual. The definition is given by W02V primary space. If psi pi belong to these two spaces, and psi ng belongs to these two spaces, phi l belong to these three spaces. Those psi and phi we the side of the psi and phi we call the solution space. Indeed, this space is as a Hilbert space by defining the normal and inner product like this. The weak form and weak solution is defined in here. For the trick pair like this, if we call this pair as a weak solution of Klein-Gordon-Schrödinger system, first the pair belong to the W space and satisfy the weak form too, like this. Quantum control is to consider the control variable by these two forms, and the optimal control defined as like this. For the many-body system 1, if needed, we define the control C star equal U star V star. We suppose U is L2 G space, that is, means we consider the control is just dependent on time and independent on the space variable. Let UAD be a non-empty closed and canvas star admissible side of U. The criteria function associated with the Klein-Gordon system is given by the cost function GC 3 like this. The first the 3 term is the system cost term, and the last one is control running cost. The detailed form is in this one. The cost function P target I psi target P target 1, psi n target G, and phi target L is belong to the V space as the target state, and psi PF and psi NFG and phi phi LC are up to the final state. The constant F01, F02, F03 are weighted constant for balancing the value of two system cost and the one running cost. In the data form is in full. From the above weak form, we can get the following theorem 1, 2, and 3. In here, we give the detailed proof from theorem 2. First, if the initial function is belong to the V space and phi 1L belong to H space, then we have a unique weak solution of the system 1. For the one nucleon and one meson case, we have people 8. Here we can get the proof for polyparticle case of the theorem 1. Next, we give you the theorem 2. For the initial function belong to V and phi 1L belong to H, then we have at least one optimal control. C star equals U star V star for the minor body system 1, subject to the criteria functions. Let's give you the proof. Such G equals the finity. The meson side is now empty subset of U. There is a subsequence CK from the space makes the CK achieves the minimums. Then the JCK is bounded in R plus. Since UAT is bounded closed and convex, this exists subset CKK can be found from the sequence CK, and the C star exists such that the convergence 5 satisfied. It means that we take KK to infinity, then CKK to the C star weakly. For the pair and the C star, the boundness of UAD, we can get this pair is bounded in W space. If we set psi star and phi star and like this, then there exists a subsequence psi CKK and phi CKK of the psi CK and phi CK and a triple pair like from W space make this a convergence satisfied. That is means if we get KK to infinity, then the pair convergence to the psi p star, psi n star, and phi star weakly. Since the medium V H is compact, then we have limited psi p I bar, psi n j bar, phi I bar. From the convergence A is 6, and the compactness impedance theorems, we deduce the form 7. The convergence CKK is, if the CKK converges the KK to infinity, then the wave function subsequent convergence the limited in L2 ZT H space. Then we get the each convergence of the term in our equation weakly in those space. And also for the phi equation, we have the convergence like this. If we set the CKK in this form, then we can get the definition of weak solution in the form 8. If we take the KK to infinity in the we form it, then we can get the limitation 9 like this. This is the limitation bar. 不在 p I bar 不在 p 不在 n j bar and phi l bar. And that is means the limitation 不在 p I bar 不在 n I bar phi l bar satisfied 9 for all the p belong to v in the sense of distribution of the Zelchi. From the uniqueness of weak solution from system 1, we have the limitation. The wave function limitation is psi pi star and psi ni nj star and phi nj star. That is means the wave function the subsequence limited to the phi star and psi star if k to infinity. It means that the wave function is convergence to this form if the c star ckk to c star. This is from 10 and 11. This is the form of a normal convergence. So we can for the each term of cos function, we have the three equation inequalities. Then from the 5 we have this form. Because the G is the weakly low semi-continuous, we have G equal this. That is means the G C star is our optimal values. C star equal U star V star is the optimal control subjected to the control function 3. This is the proof of the theorem 2. The last theorem 3 is quantum optical C star for many body Klein-Gordon-Schrödinger quantum system and subject to cost function is characterized by the spontaneously optimal system as 12. Here is the optimal control Vi star and this is VL star optimal control. Next, this is a joint system corresponding to the system equation 12. Here is the optimal control C star at the terminal values of QLT, and here is C star at the terminal value of the PPI and PNG. The last one is the necessary optimal conditions, and like this. For the detail, we can get the optimal control in the form of C star equal U1 star, U2 star, UNP star, V1 star, V2 star, and VNM star. Next is our conclusions. In summary, our work is to control interaction of minor body particles of Yuga coupling in the form of a Klein-Gordon-Schrödinger quantum system. Control Pauling nucleons and mesons is to investigate the existence of quantum optimal control of quadratic cost creature function. Further, we get optimal system consists of forced out necessary optimal condition. Our future work is interested in the interaction particle in the theoretical computation and experimental issues. Our papers and book 19 would be a confident insight in this direction. It would become convenient to do those problems. Computation is sure to our obtained theoretical conclusion. Numerical approach in the case of two and three dimensions. To do laboratory experiments would be a good advantage for our theoretical results in collaborating at the physics and chemistry fields. All of these issues would be interesting in the future. In here, we give full gratitude to 16th IFAC workshop on control application of optimization 2014 for the work to join the conference by Skype. Thanks to the GSIMs for our formal work on quantum control in cell and interaction particle at the annual conference 2009, and also thanks to Professor Shinichi Nakagi, Kobe University. Here is our reference for support of work. The next, we have published a book for your reference. Please give me your question and comments on this work. Thank you very much for your attention.